Hello, today I am going to talk about material science. In that I am going to discuss about the review of classical free electron theory. This theory is also known by the name Drude-Lorentz theory. So here I am going to talk about first the free electron concept in metals. So what are the free electrons? The free electrons are the electrons which are available in the outermost orbit in an atom, which are also known by the name valence electrons. And what is the characteristics of these free electrons? These free electrons are the ones which are responsible for the conductivity of the metals. We know that you take a metal wire and apply potential difference across it, we know that the metal wire conducts. The conductivity is due to the presence of these free electrons in the metals. Now if we take the case where the applied field is not at all there, or the applied field is zero, in this case we see that these free electrons are moving with thermal velocity. We call it as a V thermal. We have to note here that this thermal velocity is random in nature, that is, it will be moving in zigzag direction. Therefore it will not contribute to the current in the wire. Now if we apply the field to the wire, you find that the electrons now move with a velocity called as the drift velocity, which I will denote it as Vd. This drift velocity is a directed one, that is, it is moving in one particular direction from higher potential to lower potential. So here we therefore get current, which I call it as a I. Now let us explore some of the basic mathematical relations that we get here. So here I am taking the example of a wire of length L and also area of cross section A, and I am applying a external voltage V to this wire. Now under this the current flows in the wire. Then I can write the current I is the rate of flow of charges, which is Q by T. And also you see here that the current I is proportional to the applied voltage, that is, more is the applied voltage, more will be the flow of current. Or we get the Ohm's law, which is nothing but V is equal to IR, the famous relation. Also we see here that due to the applied field, there is a electric field developed inside the conductor, and that electric field developed, we can write it as the applied voltage divided by the length of the conductor. This is the relation between the applied field and applied voltage. Now the resistance of the wire R is proportional to the length of the wire. The more is the length of the wire, more will be the resistance. Also we see that the resistance is inversely proportional to the area of cross section of the wire. Therefore we say R is proportional to L by A. Or we get R is equal to the constant rho into L by A. This constant rho is nothing but the resistivity of the wire. Now the another parameter we can write here, that is conductivity sigma, which is the reciprocal of the resistivity. 1 by rho is equal to sigma, and therefore we can write it as L by RA. Now we can see here one more term used, that is current density J. Current density J is nothing but current per area of cross section I by A, which is given by sigma into E. This is related to the conductivity. The current density J is related to the conductivity sigma and the applied field E by this relation J is equal to sigma E. This equation is nothing but an alternate expression of the Ohm's law. V is equal to IR, which we said earlier. V is equal to IR and J is equal to sigma E. Both are one and the same. Now here we can also talk about the units involved for these quantities. Here if we take I, rate of flow of charges, charge is coulomb. So I is the current, which is having the unit amperes. V, the voltage, is expressed in volts, and resistance is the unit having the unit ohms, and resistivity is having the unit ohm meter, right? So you can see it all from this equation. Resistivity is having the unit ohm meter. Conductivity is the reciprocal of resistivity, therefore it will have the unit per ohm per meter. Current density is current per area of cross section, therefore it is ampere per meter square.